All right, so we're looking at Chapter 5, Section 3, definite integrals and antiderivatives, and I'm going to go ahead and be honest because I know you guys are going to react to this. I don't know who this baby is. This picture was taken by the guy that put the slideshows together, and it's always a laugh when this thing comes up, and was always in class. So I don't know. I don't even know how this applies to definite integrals and antiderivatives. So just moving along. All right, now page 285 of your book gives rules for working with integrals. The most important of which, more specifically, it's not really rules as much as it is properties of integrals, much like we had the properties of those limits way back in Chapter 2. But the most important ones are this. If we have the integral from a to b of f of x dx, if we swap our upper and lower bounds, then it's going to have the exact same value if we reverse the sign, or if we change the sign. So, in other words, flipping the upper and lower bound changes the sign of the actual value. So if you knew that the integral from 1 to 2 of some function was equal to 7, well, if you did the integral from 2 to 1 of that same function, it would be negative 7. And you can use this in a lot of different ways. You can use it as far as just changing the sign of the number. You can actually, if you need to flip these, just throw a negative out front, and you solve the problem for you. Okay, the second one is the fact that we actually used in section 2, it's the integral from a to a of any function is going to be 0. If we start and end at the same point, there is no width, therefore there cannot be any area. So if the upper and lower limits are equal, then the integral is equal to 0. All right. The third one says that if we have a constant multiple inside of our integral, we can actually move that thing outside, much like we did with the limits. So the integral from a to b of k times f of x dx, if k is a constant, we can move that k outside so it doesn't clog up or make our integral, our antiderivative that we're looking for, seem to be any more difficult than it actually is. All right, number 4 is very much again like our limits. If we're taking the integral from a to b of the sum of two functions, we can split that thing up, and we did this in the last problems on the last section. We can split it up, and notice your bounds stay the same, still going from a to b of f of x dx plus the integral from, once again, a to b of g of x dx. It makes it a little easier for us to split the thing up. Now, guys, I'm going to be honest, there's a lot of times we don't physically split it up, but we split it up in our heads. When we have like a polynomial or something we're taking the antiderivative of, we're actually going to end up thinking about it term by term, just like we were doing the integral of the first one, the integral of the second term, integral of the third term, and we never actually write it out split up at all. But we do it in our head. And this also works for subtraction in the same way that it does with addition here. All right, so that is where integrals can be added and subtracted. Now the next one tells us that intervals can be added or subtracted. So if we are going to find the area, or going to find the integral, same thing essentially, from a to b of f of x dx, and we're going to add the integral from b to c of f of x dx, well, that's going to equal the integral from a to c of f of x dx. So with that one, we're looking at the picture, and we're thinking about it like this. If we integrate from a to b, we're finding that. If we integrate from b to c, we're finding that other one, and then that's just going to be equal to, if we add these two together, the integral from a all the way over to c. Now, the average value of a function is the value that would give the exact same area if the function was a constant. Now, for some reason, this throws a lot of people off. Be careful about getting the average rate of change and the average value confused. The average rate of change is the slope of the secant line. The average value, we're actually going to have to do some integration here. So if we were going to find the average value of this function right here over the interval from 1 to 3, we would need to find out what the actual area under this curve was. Now, we've got our power rule thing here we can use. So we're going to end up adding 1 to get 3, dividing by 3. So that means we're going to end up with 1/6 x to the third evaluated from 0 to 3. And then, of course, we can plug our values in and all that. And we end up getting 9/2. All right, so that is the area, the shaded area here, this gray or this tan area. And what we're looking for is we're looking for what would the value have to be if we were to have a rectangle which had a constant value from 0 to 3 that would have the exact same area. So the way you do that, you find the area under the curve, as we did here, and then you're going to divide it by the width of the partition or of the interval. So the width here is 3 minus 0. So we're going to divide 4.5 by 3, which gives us 1.5, which means that right there, if we were to draw a line across here, a constant function, and then shade underneath that over the same interval, this red shaded area has the exact same area as the tan area we calculated earlier. Because 1.5 times 3, the height times the width, gives us the exact same area we found over here under the tan, sorry. I don't know why I'm seeing that as gray. It's actually not. I'm not seeing it gray. It's just looking, no, it's not even looking, I don't know. I'm just calling it gray. So the average value, easy way to find it, is just the area under the curve divided by the width of the interval. And the way you find that is 1 over b minus a times the integral from a to b of f of x dx. And b minus a, remember, is the width of the interval. And then that's the same thing here where we're integrating from and to. So the area, which is found by the integral, and we're dividing by the width, which is 1 over b minus a. And remember, don't get every average value mixed up with average rate of change. They're two very, very different things. All right, now the mean value theorem for definite integrals, yes, there's another one. Now this one's not used anywhere near as much as the derivative one. Says that for a continuous function, at some point on the interval, the actual value will be equal to the average value. So looking back at our problem right here, the mean value theorem applied here would say that the average value and the function value would have to be equal somewhere in the interval. Well, they're equal right there. So you can see all it is it's saying that there's somewhere in there where the average value, the integral divided by the width, has to be equal to what the function value is at some point in there. So that's that point right there. Now, this mean value theorem also is going to be one of those where it has to be, the function has to be continuous. So there is your mean value theorem for definite integrals. If f is continuous on the closed interval from a to b, then at some point c in a to b, f of c, the function value itself, has to be equal to the average value that we were calculating. All right, the average value of a function f on a to b always lies between f of a and f of b. Well, think about sine x on the interval from 0 to pi. Sine 0 equals sine pi, which is equal to 0, but the average value on the interval is greater than 0. So it's not always going to fall in between the two y values. So that's a false. All right, if the integral from a to b of f of x dx equals 0, then f of a equals f of b. True or false, and justify your answer. Well, here's the thing. You're saying that the area under the curve equals 0 only when the y values at the beginning and the end are equal. Well, that's not necessarily the case. Think about that. We can start here and end here. Y values are going to be the same. Ignore the fact that I can't draw a straight line. But what do we know about the area under the curve? Well, that's definitely not 0. Not 0. Now, this would be the case for the average rate of change. Yes, it would. But it's not going to be that way for integral, so this is false. If you did the integral from negative 3 to 3 of 2x dx equals 0, but 2 and negative 3 is not equal to 2 times 3. You can have integrals that are equal to 0, but it doesn't mean that these two things have to be equal. The only time that those two things are going to be equal and you're going to have an interval, well, sorry, no, it's not going to be the only time, but one of the few times is where you have, you would have to have area above and area below for it to be equal to 0, or it would have to be a horizontal line at 0. So false. All right, if the integral from 3 to 7 of f of x dx equals 5, and the integral from 3 to 7 of g of x dx equals 3, then all of the following must be true except which one? Now, I want you guys to look at these. I'm gonna ask you to pause the thing, look through this, and find the one you believe is correct, or sorry, is that not true. And it turns out it's this one. Now, the thing is, what do we know? We know that the integral from 3 to 7 of f of x dx equals 5, and the integral from 3 to 7 of g of x dx equals 3. Well, we're looking at the properties that we talked about at the beginning of the section. Which ones are true, which ones are false? Well, we can do integral from 3 to 7 of f of x plus g of x, split it up, and it's going to be 5 plus 3, which equals 8. So that one checks out. So let's do all the other ones, and we'll come back and tell why that one's not. And then this one has the constant multiple. So the constant multiple we could move out front. So 2 times the integral from 3 to 7 of f of x dx. Well, f of x dx is 5 integrated. So 2 times 5 does give you 10. We could do the difference again. And the integral from 3 to 7 of f of x dx is 5. And the integral from 3 to 7 of g of x dx is 3. So 5 minus 3 does give you 2. Checks out. Now with this one, you got to be careful because we're actually flipping this around. Notice your bounds. And the integral from 7 to 3 of g of x is actually going to be negative 3. And the integral from 7 to 3 of f of x dx is going to be negative 5. So we have negative 3 minus a negative 5, which gives us a positive 2 yet again. So by flipping these over, that's going to make this a negative 5 and a negative 3. So our answer still works out. Now what about this one? Well, if you remember, there were no properties that dealt with the product of two functions. You had the sum and the difference, and you had a constant multiple multiplied, but you didn't have two functions multiplied. And there's a reason why. Well, remember how difficult or how much more involved it was to find the derivative of two functions multiplied together. You use the product rule. Well, guess what? We're going to have a similar rule to do the antiderivative of this, and it's not just integral of f of x times the integral of g of x. So that's why this one is a no-no. Does not work out that way. All right, so you guys try this one and see which one is not going to be true. Pause the video, work it out, and then come back and we'll explain which one is and which one is not true and why the other ones are true. All right, so here is the answer. The answer is D. D cannot be true. And we'll talk more about that in just a second, but let's talk about the other ones and see why they are. Well, this one, the integral from 2 to 8 can be broken up into 2 to 5 and then 5 to 8. Remember, we can add intervals. And that means we can break it up and do the integral from 2 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx, which gives us 12 plus 4, which is 16. So that checks out. Right, with this one, we've already got it broken up, but we have a constant multiple over here that we can move out front. So the integral from 2 to 5 of f of x dx is 12 minus 3 times the integral from 5 to 8 of f of x dx, which is 4. 3 times 4 gives us 12, and 12 minus 12 gives us 0. So that one checks out as well. Part C, the integral from 5 to 2 of f of x dx, we just flipped our upper and lower bounds, which means that just changes the sign over here. So it is negative 12. Let's skip D and we'll come back. And then E is nothing more than what we wrote for A up here. And the integral from 2 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx is 12 plus 4, which is 16. Now, let's look at D. D says the integral from negative 5 to negative 8 of f of x dx equals 4. Now, that's trying to use this one right here, but changing the signs of the upper and lower bounds. Well, there's only one problem here. You got to think about what we're actually finding. When we know this part right here, we know that when we go from 5 to 8 and we find the area under some curve that's up here, this area equals 4. And what this is saying, it's saying that if we go from negative 5 to negative 8, negative 5 to negative 8, over here, we're going to get just the negative value. There's only one problem. What do we know about the function over here? We know absolutely nothing about what the function's doing over there. If we could be guaranteed that this thing right here was symmetric over here, then that would be true. It doesn't say anything about that, though. We don't know what this thing does. This thing could go up like this over there, or it could go down like this over there. It could do crazy things over there. We know absolutely nothing about this function between negative 5 and negative 8, so we can't make any kind of judgment on what the value of that thing would be with the information we have. So be careful about assuming things and properties that are not true. This is talking about specifically between 5 and 8 on the x-axis. This is talking about between negative 5 and negative 8. We don't know anything about what's going on over there in the negative side. So that's why this one is not true. Well, it could be true, but it does not have to be true. It's a very special case where that thing would be true. And like I said, it would have to be the one where it was symmetric, but we don't know that. All right, what's the average value of the cosine function on the interval from 1 to 5? Now, this would be a calculator problem, and if the decimals don't kind of give that away, I don't know what would. But let's go ahead and pull up a calculator here. And I'm going to clear this out. And let me move this over here. and we're going to find the average value of the cosine function on the interval from 1 to 5. So remember let me do this a little different here. I'll go ahead and open this up, and now I'll do the calculator. Remember that when we do the average value, it's 1 over b minus a times the integral from a to b of f of x dx. So when we plug everything in that we've got here, we're going to do 1 over 5 minus 1 times the integral from 1 to 5 of cosine x dx. That's what we want to put in our calculator. So we're going to go ahead and do the 1 over, and I'll do the subtraction there. I'm even going to do it as a decimal, 0.25 times, now I'm going to show you how to do the integral on the 84 here. It's alpha and window, and you're going to do function integration number 4 there. Then all you've got to do is fill in all the holes here. So 1 to 5 of cosine x dx. And then hit enter, and you end up with negative 0.450098814. And just to double check, it is one of our answers, but just to double check, I'm going to check and make sure that I am in radians. Yes, I am. Okay. So that's my answer, answer B. All right, if the average value of the function f on the interval from a to b is 10, then what is the integral from a to b of f of x dx equal to? Well, here's the thing. Remember what we've got. This is the average value. So we have 1 over b minus a times the integral of a to b of f of x dx, and we know that this equals 10. So if we want to find just what this thing right here is, what are we going to do to both sides to get rid of this? We're going to multiply both sides times b minus a. B minus a over here, b minus a over here. These are going to cancel out, so I've got just the integral. So the integral from a to b of f of x dx is equal to 10 times b minus a, or 10b minus 10a, which is C. All right, that's all that section. Talk to you soon. Make sure you make note of any questions or problems you might have, and we'll talk about those first thing.